My name is Gwen Shapira, Chen Shapira בעברית. I'm going to talk about how we use the Kafka and Kafka-related technologies to build fraud detection architectures. I already introduced myself, but I want to also introduce this book I'm writing. At the current rate, it will be finished about never, but we are putting in new chapters about once a month. It's just that Kafka keeps adding stuff faster than we can actually write about them. We're going to talk about anomalies and how we detect anomalies and the architectures that we build to detect anomalies. And because my architecture is highly streams-based, I'm going to talk a bit in general about streams and the technologies we use to build them. So some of the anomaly detection architecture problems that we try to solve is credit card fraud. That's pretty trivial. Bad people steal credit cards and then try to use them to buy things on the internet. It's bad for credit card companies. It's bad for retailers. Everyone is trying to catch them. Pretty straightforward. Health insurance fraud is a big deal. And the specific case I worked on, I don't know if you know, in the US, abuse of prescription drugs like opioids is a huge, huge issue. And apparently, you can detect them if you know a lot about what your patients are trying to do. So things like pharmacies that people try to get more opioids from, doctors that prescribe too many opioids, patients that switch doctors every 3 days and try to sell stories. We have a lot of data. We try to catch bad players in that place as well. So how do we detect basically, to detect fraud, we are looking for things that deviate from normal patterns. It's good and bad. I mean, that's how we detect fraud, de facto. It's bad because if you're just a weird person, you'll get a lot more strange looks from doctors. My younger brother tried to buy shoes from a US website, shipping to my house using his Israeli credit cards. They denied his transaction because apparently being in the US using an Israeli credit card is suspicious. How do we actually detect fraud? It's actually pretty embarrassing how simple technologies are effective. So the main way I've seen that people detect fraud, the algorithms are obviously secret and belong to the credit card companies and the insurers that I worked with, but it's all about counting events and adding stuff up. By counting and adding, you can do averages. If you have averages, you can do standard deviations, and then you can find anomalies. That's more or less the key. There's a lot more, obviously, and people do clustering and k-means and all that kind of stuff, but it all comes down to counting stuff and adding stuff up. So what do you do when we think that we detected fraud? The systems I built are built on a model that's similar to the way our human brain operates. So suppose you go and play a game of tennis. Obviously, while you're playing, you can't think all that much, right? You're busy jumping around, waving your hands. So you rely on muscle memory. Your eye and hand is coordinated, hopefully, if you're a good tennis player, unlike me. And it's just your body, you don't think. Your body does the right thing at the right time. But in between sets, you stop for a bit and say, oh, this opponent seems to prefer this side of the court. He only does short balls, whatever. So you can actually do some analysis, not too much, because you only have a minute or two and you're tired, but you can do some stuff between sets. Most of the relearning happens completely offline. There's weeks of practice and training and watching videos of yourself and other people play in between competitions. That's where most of the learning happens. And we do the same thing. So in programming, we have 3 very common programming paradigms. Obviously, there's a lot of programming paradigms. I'm looking at in how we react to inputs. So if you are doing request response, as in your web service gets a request and responds immediately, it has to be within microseconds. And that's similar to the muscle memory. Not much analysis can happen in that time span. If you are getting a request and you kind of asynchronously process it, and then you have a few minutes to do something, and then you react a bit later. That's kind of stream processing, similar to the syncing between sets. And then doing training sets, which can actually be like weeks or months of work of data scientists, that happens completely offline, and that's kind of like the reflections that happens between competitions. So we have request response, streams, and batches, which we use for in case of credit card transactions or pharmacies to immediately reject a request. or set an alert and stop the purchase a few hours later or a few minutes later. Dashboards, most of the updates of the counts happen asynchronously by stream processing systems, and then building the models, training, and having humans review some stuff, that's obviously similar to reflection. So, the architectures we build. It's usually a mess these days. Once upon a time, architectures was really easy. You would buy a large Oracle database, and you'd install it, and you had an architecture. You'd write a lot of Java code to work with Oracle. That was fairly straightforward. No longer the case. We have a lot of technologies to choose from, and it's frankly a mess. And what usually ends up is that people end up with something like the Lambda architecture. If you're here for the Flink presentation, you want to do some stuff in real time, but then you don't know if real time is actually that reliable. What if I'm double counting? What if I'm missing counts? So you also have a batch process to kind of fix up what you do. Very obvious downsides, you're doing everything twice, you have your code twice, you have to monitor things twice. And when we actually built, that's kind of my first iteration of a fraud detection architecture. Don't worry, it got a lot better. And you can see how many components, and you have to monitor all of them, and you have to make sure that all of them are up and running, or unless you're using the Hops Hadoop, which monitors it for you. It's just very, very difficult for just finding bugs. Suppose that something went wrong. What do you know about who actually caused the issue? Super messy. We're trying to move away from architectures that are that complex. The reason we ended up with those is that back in the day, no single system actually did enough. So Spark really didn't do enough, and HBase didn't do enough, and HDFS didn't do enough. So we had to put them together to address different parts of the problem. These days, we're trying to simplify things. So we're using fewer components, and therefore able to use more fun tools when drawing them. So we do have the web app send events directly to an Apache Kafka, do all the stream processing on top of Apache Kafka, send all the information, or at least a lot of the information, to a data warehouse, the data warehouse is not necessarily like Teradata. It can totally be Hadoop or HBase or Kudu. Kudu, I heard, is the latest and greatest in data warehouses. And then you have the training applications and humans who can look at the data. And eventually, the results of the training go back to Kafka as updates to the model. So how does it all work? How can we actually build a system that is that simple? How many of you already know Kafka? OK, I can go really fast over this part. Looks like a lot of you kind of know Kafka. Kafka is all about logs. And we're talking about logs that are more similar to a database transaction log than an actual text log, although the idea is similar. You write something, and you keep on writing sequentially to the same file. This is very efficient in terms of disks and resources and so on, and that's our basic premise. And we have the concept of a topic, because Kafka is a pub subsystem. And the topic is just a collection of partitions. It's a logical collection. We try to make sure we have the same schema in all the partitions, but you can have different schema for each event, and it's also fine. It's just a logical sharding, or a logical collection of partitions. And the idea is that you produce events to a topic, and then someone consumes the events from the topic. You can have many, 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 many consumers for the topics. That's like the big Kafka strength, is being able to have a lot of systems reading from the same topic. And you can scale consumption. So each consumer can read one partition, it can read more, and if you have multiple consumers that belong to the same logical consumer group, they will automatically load balance and do high availability between them. So if you have 100 partitions in a topic, you can theoretically have 100 apps sharing the load of processing the events from those partitions, which gives you very nice scalability properties. It also means that if something bad happens to one of your application servers, it just crashed, another application server will automatically and seamlessly just take over. So that's kind of cute. Another thing I think I don't have a slide for, but you can actually, consumers basically track their offset in a log. So we talked about logs having offsets. Each consumer knows that, OK, I've read event number 5, I have to read event number 6, now event number 7, and so on, which means that consumers can also backtrack in order to do reprocessing. If you're here for the Flink presentation, reprocessing is very important. Sometimes you get something wrong and want to fix a mistake. Sometimes you have a completely new algorithm that you want to test out, so you can kind of move back and try it on existing data. Low compaction is our attempt to treat data in Kafka as more of a key value store. So the idea is that a lot of time the events in Kafka are actually represent updates to a table in a database. So you're getting an events from, say, Oracle or Cassandra. A lot of them would just be the same row with the same primary key, just having different things that happen to it. A lot of time you're not really interested in all the history. You just want the latest state or the latest 3 states or the latest state plus everything that changed in the last day. Kind of like, in a database, you have the backup and then you have a bunch of redo logs to be able to roll it forward to specific points in time. Kafka basically gives you the capability to do exactly the same. So that was the storage part, but what about stream processing? Well, we see stream processing as having two different paradigms. Some people treat stream processing as really, really fast MapReduce. So you send the job to a different server, it runs, and you pick up results from a different server. That's legitimate, and it's very good for analytics. You have a data scientist, it gives work for a remote server, and you pick up the results. But there's also a paradigm that you have those microservices that are just web apps that continuously process results. So asynchronous, event-driven microservices. And so if the first one, if you look at Flink and Spark streaming would be you send the job to a different cluster. If you look at things like Akka streams or reactive architectures, those would be, you just put the stream processing in your own app, you just allocate one set of servers to your own app and go from there. We believe that stream processing is a very basic paradigm of how businesses work. Sales don't happen in batches, people continue buying things. Shipments don't happen in batches. Things happen all the time. So, and most of the time you don't need to respond to them immediately, but you can't really respond to them just once a day. So you need to have this in between asynchronous processing of things that happen. And all the things that we do with stuff that happen, we call them derived views. It's give me a view of everything that is fraudulent out of those events that happened, for example. Stream processing is fairly simple. You consume events, you do stuff to them, and you produce. And do stuff is where you should write your code. You should not have to focus about the consume and produce part. That's our job. But it should be easy. It's not, people sometimes make a big deal out of stream processing. It should not be a big deal. On the other hand, there is a lot of kind of edge cases and conditions and stuff to worry about, right? If you do something like a window or a join, it means you have a local state. You need to maintain caches. You need to worry about what if a machine crashed, will all its state with it? How do we recover? So we do want to have a system that takes care of those paradigms. And when we built Kafka Streams, we basically built a system where we can have, you can basically say, okay, I'm getting data from this topic, I'm joining it with that topic, I'm doing a window every 5 minutes, and I'm writing the results over there. And we want to have Kafka Streams basically take care of all the nested details. Kafka Streams has an embedded RocksDB in order to maintain arbitrary sized state. Obviously, arbitrary sized will immediately drop in performance if you have more states than memory, which is why you can actually keep on adding more and more of those processing tasks. We will always have a processing task per partition, but you can have all of the processing tasks in one process on one machine, or you can add more and more machines and continue scaling, kind of the way we do for consumers. If you're here for Flink, the notion of time is super important, and we always have two notions of time. There is the time the event got generated, and the time the events got processed. And a lot of stream processing systems, not Flink though, kind of tend to mix them up. And you really, like if someone just went to your website, but before you managed to send the event to Kafka, he ran out of battery and he reconnected 6 hours later, you really don't want the event to go into the current batch. You want to re-update you already calculated an average for the window for 6 hours ago, but you want to go in and do an update. If the data went to a database, you want to do a database update. If the data went to a Kafka topic, you want to put in a new record that will later become the latest and greatest source of truth with the new results for something that happens 1 hour ago. The core principle of streams is that data never stops arriving, and you have absolutely no control over when do old events show up. It's just a fact of life. That's how Internet of Things is going to be. We are building systems to handle it. So all this is very nice theory, but how does it actually work? How do we actually do anomaly detection with all this? So our idea was that we send everything into Kafka. So we send the events for the people who went to the doctor who prescribed the drugs, when did people refill the prescriptions, a lot of information. We also, in addition to events, we also have user profiles. This is things like where does a person lives, where does he go to work. Why is it important? Because if he lives in one place and goes to a doctor 100 miles away, this is super suspicious. If he goes to 3 doctors, all of them are 100 miles away and in different directions, it's super, super suspicious. So we need to have information about the user. Same thing for credit cards. If someone lives in Russia, he's immediately suspicious. Sorry, now I'm guessing that half the audience here is recent Russian immigrants. I'm sorry. China, it was China, really. Okay. In addition, we have rules, right? I mean, when you do machine learning, usually you end up with features, and you have all sorts of values that you want to test against. Is the distance over 100 miles? Are these things close to the center of the cluster by a certain threshold? Do they have more than 20 transactions in different locations in the last 5 minutes? All those things are rules, and we want Kafka to cache the rules, to cache the profiles. Everything has to be in the cache of not just in Kafka, the application, when it starts up, it goes and reads those topics from Kafka and stores them on cache, so when the events show up to your web application, it can respond really, really fast. All this stuff should be cached. And because there is, again, limited memory per machine, you want to partition the events and the profile updates, and if relevant, also the rule updates, based on the same keys. So one machine can say, I'm only processing events from this partition. It will contain those user IDs, and those are the user IDs I have in my the profiles for in my cache. Those are the user IDs I have the relevant rules for, and so on. So you have all the state in memory, and you just respond to events as they come in as soon as possible. And you keep updating Kafka with results of stream processing. You keep, as events come in, you can keep updating the history of each user with the new events. And you also make decisions. And you can feed back the decisions you already made back into Kafka and the reasons for the decisions, and it just goes in as a feedback loop. And then out of Kafka, you obviously get results. Things like, oh, please send an email to the guy saying that we rejected his transaction. And you also want to put all the data into some kind of a data store. So a human or one of those, at some point you may want to use the decisions you already made and some information about how they ended up. Did many users dispute? Did you have many issues because you rejected too many? You want to have it back and have either humans or machines look at them and reevaluate the rules. 10 minutes? Okay, cool. And one of the features you have to note that I really, really like in our architecture is that the rules update goes to Kafka, which means that your app consumes them. One of the biggest issues we always had is that you're caching the profiles and the rules. What do you do with they changed? If some admin goes into the database and modifies the profile or modifies the new rule, you have to keep polling and looking for it. And polling a database is fairly expensive. If you're consuming from the Kafka topic, those new changes will show up, and your application probably has some kind of a thread to update the cache. Cache invalidation is a really hard problem, so we were very happy that our architecture had a good solution for it. So why do we think Kafka is a really, really cool fit here? Obviously, the use of partitions for scalability, being able to partition everything by a region, or by user ID, or by credit card ID, and so on. Using the Kafka consumer model, so when the system was small, we had very few consumers, and you could scale the number of consumers. And the nice thing, the consumers are completely stateless. The app is stateless. All the state is in Kafka. So you can use stuff like Docker and Mesos and Amazon Cloud to just scale up and down. It's not just in theory. We have customers who use Docker to really scale consumption up and down in times of day. It's really cool. We use Kafka to provide reliability to stream processing. The state in RocksDB is backed up by Kafka. So if a machine crashes and the RocksDB completely goes away with it because it was one of those Amazon disappearing machines, you put up a machine, it immediately refills the RocksDB state from changelogs written to Kafka, and we're back in business. Because of the intensive use of Kafka, we didn't have gazillion systems to maintain and monitor, and the cache and validation thing, which is really cool. And that's kind of our vision to the future, really, is that we have a lot of applications always pushing data to Kafka asynchronously without hurting the request response performance. And those it could be your apps, it could also be databases. MySQL is probably the most popular source. And then you put a lot of stream processing applications on top, and you can have as many as you want because Kafka supports a lot of different consumers. And you also put data into Hadoop and data warehouses for kind of offline processing. That was really, really fast. I'm wondering, we have time for questions, all right?
How much data, like in this vision of the stream data platform, do you actually see Kafka as the storage holding all the data to the past, or do you see it as a transient storage that holds? And if it's transient, how much?
Okay, so it's always a question about what is the source of truth for the organization. And even, no matter how much I want Kafka to be a source of truth, realistically, data warehouses have been trying to become the only source of information for many years and failed. I don't think Kafka is going to do much better. But we do think that there is an economy of scale, and you can get a lot of benefit the more data you have in Kafka. So we are trying to support the vision of having everything in Kafka, knowing that this is kind of futile because it has been futile every time in the past.
Does or will Kafka Streams provide an API, or like higher level API for stateful processing?
We provide a very nice API that looks exactly like all the other stream processing APIs. I think we kind of converged. I mean, Spark Streaming, Flink, Kafka Streams, they look very, very familiar. You shouldn't have to worry about any type of safety. That's one of those things we actually try to do behind the scenes for you. So right now, Kafka Streams is at least once, and we're working really, really, really hard to add exactly once. And you may have, because there is a lot of trade-offs, you may have at least once, exactly once, switch to choose from, but it's not something that you should have to think about all the time when you're writing code.
Why do we need so many streams projects in Apache right now? There's like 3 at last.
I think it's because we don't really agree on a lot of things. I mean, if we totally bought onto the Flink vision of do everything in a separate cluster, we would have probably supported Flink and not started our own. Same for Samza. The only reason that we have Kafka Streams and not just using Samza, and I mean all the people who wrote Samza work for our company, so we could have totally done that, is that Samza has really, it's supposed to run on a separate cluster. It's integrated with Yarn. I'm not a huge fan of Yarn. I'm sorry if there's any Yarn developers here that I'm hurting. So we kind of have a different vision of how we want to do things. We wanted the lightweight library that just provides an API and few semantics and let Kafka do everything. Spark Streaming was not willing to let Kafka do everything. They want to say, oh, we can actually use all those different sources, not just Kafka. So they had to do things a lot differently. I don't know if Flink is ready to say, oh, all data always comes from Kafka and we'll use Kafka semantics. So we had a different vision. We started a new project. And I think that's true for everyone who starts a new project. He thinks he can do stuff better, and he thinks that he's right. And I'm Israeli, so obviously I feel that our way is our way or the highway, no compromise. We know what we're doing. Everyone else will find out.
So we'll be back here. Thanks, Gwen, again.